My name is Dima Kniazev. I'm a software engineer at Redis. And today I'm going to be talking about using Redis as online feature store for real-time inference. I think Nick, he has mentioned in his prior talk about the feature store in general. Redis is not a feature store, so it's not a competitor, but we'll touch upon feature stores a little bit. Um, and the whole goal of this conversation is to basically put Redis as a building block for serving real-time machine learning models, basically. So I'll talk a little bit about Redis in general. So Redis itself is an in-memory database, and I'm sure many of you are familiar with Redis already. Many developers use it as a caching mechanism, as a key value store to bring in the data from, slower data sources like relational databases, maybe data warehouses, and then, put this into in-memory key value store and then basically have quick access to the data essentially. And so Redis itself is an open source product, but Redis company commercialized this in a different product, which is called Redis Enterprise. It can be deployed to pretty much any cloud, any platform. You're probably familiar that Redis is not just a key value store, so you can create various types of data structures in there. You can create hashes, you can create, sets, sorted sets, geospatial data and such. So it's not just, putting a key like a string and then feeding it back. In the commercial version, you can also use JSON. You can use it as a search mechanism. You can create secondary indexes and in there as well. And you can use, more complex structures like graphs, for example, or Redis Bloom filters. And so when would you want to use Redis in general and Redis Enterprise in particular? Well, for pretty much anything that requires real time. Right? I already mentioned, that many developers use it as a caching mechanism, but, typically for mobile applications, for inventory management, financial applications is a huge space for us. Gaming is a huge space as well, because you probably want to keep a lot of data in memory as well. And of course, recommendation engines. As you browse in, there's a whole bunch of algorithms that are working. Whatever is your favorite website. And a lot of the data sits in memory and stored from in-memory databases. Real-time machine learning. I'm not a data scientist myself, so I'll be showing the demonstration, but certain pieces on how to prepare the and train the model itself, how to prepare the features for those models. It's a magic that typically data scientists do. I spent a lot of time working as a data engineer. So basically was in the position of preparing that data for data scientists. And so I can tell you that this is a big pain to kind of work on the ETL data pipelines that collects your data from multiple sources. Maybe some data is sitting in the files and S2 storage. Maybe other data is coming from a SQL database or maybe some other databases. You want to collect all of these different data sources and you want to funnel this data to a data scientist who only want to use 10, 15 columns out of this in a denormalized, nicely shaped way, and then use it for training and preparing their models. So, so if you want to learn a little bit more about, how to use feature stores, like the full tutorial of that, I got the link on the blog post for you. So the very first link here will walk you through the process of, building this model using the feature store. And then the second link is basically about when would you want to use machine learning models in a real-time manner, right? And part of the reason that real-time models have become popular in the past couple of years is because of COVID, of course. We stopped going outside at some point, and then we started to use technology more and more. Mobile banking, web applications, all of this is, gaining a lot more traction than it used to be in the past. And so financial area and gaming are the two, main industries that are really focusing on transforming whatever the prior process to preparing data and serving data. For the models, it used to be batch oriented, and it's now more real time oriented. And what that means is that if you apply for a loan, for example, you want to almost immediate um, result to get back to you, other than just submitting your data and then waiting for 2-3 days before someone will call you back and say, "Hey, your loan got rejected," um, because of the number of things. So the third link here is the link to the repository that I shared before this meetup. It's a loan approval demo. And the story behind this demonstration is actually quite interesting. So it originated from the company called Tecton, and Tecton is, a group of folks who actually contributing to the Feast, which in turn is the open source project that implements the feature store, right? And we'll talk about the feature store, and we'll try to unpack this a little bit in the next slide. But and so they also have, so Feast is an open source project, but they also have their commercial version. It's called Tecton, and it has all of the different steroids, of course, the nice GUI and a nice, additional features on top of Feast, because if you run Feast out of the box, you probably get confused, even though there is a whole bunch of documentation. So many people get confused who start using Feast in the first place, but Tecton is very different, of course. And so they originally created this demonstration to test Feast against the DynamoDB, because you need some data to be served to the model in order to make sure that it can work in the real-time manner. And of course, at Redis, we pay a lot of attention to latency in any form and shape. And so we decided to partner, and we created the connector from Feast to Redis. And so we tested, actually folks at Tecton, they tested the, how to use Feast with Redis as an online feature store. They got very good results. They have a separate blog post on the results. And then we started to adopt to kind of show our demo how Feast can work on Redis to serve real-time models. And then I'll also show an application that was built with Streamlit. I think Nick mentioned Hugging Face in his presentation. Streamlit is what he said is a lot more complex. I don't think it's really complex, but you'll have a chance to explore if you just go to that repository. There's a full source code for that as well. So why online store? We started talking about this, and so the typical pipeline or the typical process to prepare the model is essentially to grab different sources of information. So in this case, for example, the zip codes and the credit history for people, and then you want to feed this into a framework that is called Feast, or something that is called feature store. You could have just feed all this data into the model directly and train your model, of course. But then the problem there is that if you start working on this, and then some data engineers and data scientists start using this data, they typically come up with certain tweaks in the feature engineering process, and somehow you ending up with the data that get fed into the model in production that was different, that essentially was used to train the model or to prepare the model itself. And so it's a very big problem because the model in production behaves very differently, and debugging or troubleshooting the model, um, for example, the neural network, well, good luck doing that. It's almost impossible. So what you want to achieve is essentially use the same shape, the same form of the data in the production and during the testing process. And so the feature store is basically designed to solve that problem for you. And the other thing is that once you come up with this feature, you kind of want to create a repository of all these data blocks that you can reuse across multiple models, so that other data scientists can use the same data, the same approach, because it's actually taken a lot of time to prepare that data and feed into the model. And so once you have this nice feature store and nice features identified, you just feed this historical data into the to train the model, and then you can start using that model. But what happens if you keep getting the new updates to this data? So for example, I trained that model and then deployed this into production, and then just after that, I went out and took a couple of other loans. So this information is not in the historical data and is not going to be accounted for, but should be, because it's a recent data that needs to be used for predictions, right? And so in that case, you can, of course, go and query for this data in the original historical data, but that takes a lot of time, right? So, it can take maybe minutes, maybe seconds. But what we're trying to achieve, the way we define real-time response latency today, is basically we want to get a sub-millisecond response time from the backend system, because then there's going to be the network latency and the internet latency, and for the end user, it's going to result into maybe a second or a couple of seconds response time. So we want to kind of get a sub-millisecond response time for the model to respond at the server, essentially. And so in order to achieve that response time, you need something different. You need to basically keep some additional information in memory. And so this is where you can start using online store feature. Feast actually has a definition of the online store. You can use DynamoDB, as I mentioned before. You can use other databases, and of course, you can use Redis to kind of accumulate this recent data which can be accounted in the prediction process. And you can keep trickling data into that online feature store, so you always get the latest data. Occasionally, you'll retrain the model, of course, using the historical data, but because it's a lengthy process, you just don't do this, every minute or even every hour, probably once a day or once a week. But the data, the recent data goes into the online feature store, and it's still going to get used for the predictions. So it makes your model accurate, and it makes it responding very quickly, basically. So let me go to the demonstration. Hopefully it works. And I'll just give you basically, I'll just give you a quick demonstration of the final result, and then we'll talk a little bit about how can we get to this final result. So this is essentially the Streamlit application. I'm not affiliated with Streamlit, but it's really easy tool. If you're familiar with Python, you can basically script something in maybe 20, 30 minutes. You don't have to learn anything about HTML or whatever. So it has building blocks that you basically compose in your to look like a real application. And so this is a long application demo. So you can see on the left. It's a framework to build small web applications, basically, or data science applications. It's essentially the same or similar framework to the Hugging Face that Nick has mentioned about. But it's more, I guess it's a little more popular. I don't know, actually. Maybe it is, maybe no, but yeah. Yeah, so you can go to streamlit.io and explore. They have a gallery. They have, a whole bunch of documentation there. I personally like it. And so you can build a quick application like this loan approval application here. And on the left-hand side, you can see that there is different boxes to put in the parameters. So those are typically the parameters that your application will collect when interacting with the user. And of course, that's not all of the information, right? Okay, my loan got rejected. Of course, I need to increase the yearly income. And so you see how quickly it responds when I change the parameters, the input parameters here. If I go back to, I don't know what's the threshold, but if I go back to some other number, my loan get rejected again. And so if I close this left-hand side, you can see that for the user input, I only input this parameters here in this table, but it actually got enriched with this additional parameters and essentially what is called a feature vector is composed, and this feature vector is then fed into the model, and the model actually uses a lot more than I input through this UI application, because a lot of this information is just sitting in memory and waiting for for the application to use it for the prediction. And so this is what makes it so fast, because all this additional information is actually, you don't need to query this from any slow database. You don't need to go anywhere. It's just sitting in there. And it's very recent data. If the data gets updated, like I mentioned before, if I go and take another loan, before the model get retrained on the regular basis, this information will get updated in the in-memory database in the online feature store, and it will then be fed into the model, and the model will say, "Oh, you now have a extra extra parameters, extra loan, so now we'll reject your loan."
Allow me to ask you to go back one step. The first step is what you entered on the left. There was like, these are the parameters on this, if you have loan task, then they ask for the loan and they keep this information about themselves.
Yes.
The second part, this one feature vector, you have to add information about, let's say, whether they did this on zip code and what's the relative on there or stuff like that. This is what we see. Right?
Yes.
So
yes.
And what you're saying is we think this is the feature vector, where this keeps it all in memory, therefore it makes it very easy to actually
Yes, that is correct. But it doesn't keep it just for this particular user only. It keeps it for a whole bunch of users, essentially. And so there's,
for example, another user does something else about this.
So other than myself, because you can see that there is the last 4 digits of social security that's probably used to, pull the additional information about that user that is now kept in the in-memory database. But how many users do you expect to serve, right? Well, that's probably a lot of people. And so a lot of this information will be sitting and waiting in memory because each of them can actually go and apply for a new loan at any point of time. And of course, you can implement certain logic, like for example, you'll see that the incremental materialization process, which is called to basically refresh this data in the in-memory database, it has a timestamp. So I can incrementally update this data in the in-memory database to not keep everything, of course, because I don't need everything. I only need the last probably a few transactions to be kept in memory, right, to be accurate. And so this is what kept in the database, because otherwise you would need to go and pull this information potentially from many different sources, because you don't know. Going back to this diagram here, for example, these two databases, it may be 10 databases that provide data for the training and for the inference, right? And those may be different, very different databases. One of them can be an Oracle database, and the other one can be a Parquet file sitting somewhere and produced by your Spark pipeline from other systems. So you don't want to basically go and pull all this information from multiple sources, denormalize this, combine into a feature vector during the model, during the execution or inference time, right? Because that's going to take a lot of time, of course. So yeah, in order to any other questions on this application and the process so far? Let me check if there's any. Okay. So how can you let me actually go back and talk a little bit about the repository itself. So this is the repository that I have provided in the description for this meetup. I can post it as well to the chat. I originally created this for Azure to be deployed on Azure. And so if you switch to main branch, you'll still see that, the older version. So if you want to play with this, please switch to local Redis branch. I'll eventually merge it to here. I just didn't want to confuse those of you who maybe started looking at this repository already. And so what this repository suggests you to do is that there's a quick introduction to the process that we just described. You can use you can use multiple databases for the online feature store. And if you decide to use Redis for that, you can also use it on Azure. You can use Redis Cloud, which is our managed service, or you can use a local Redis database, which is actually what I'm using in this demonstration. So if you decide to use local Redis, which is the easiest thing, what you can do is just pull the Docker container and run it. And this is what I have running on my computer here. This is the Redis stack container here. And then you just go ahead and create the virtual environment, activate, install the dependencies, not interesting stuff. In the document that is called feature store YAML, which is the configuration for the feature store, you just put the connection string for the online store to localhost 6379. And then the first step that you typically do is that you initialize the Feast repository. So the Feast repository is where Feast keeps all the definitions about the different features and entities and data sources that you keep, that you use to construct your feature vector. And then you materialize your data this is essentially the step where you load a lot of the recent data into the Redis database. So then you train your model, and training the model is essentially reading some historical data. In this particular case, it comes from a bunch of Parquet files. They're also stored in the repository as well. So if you look at the cloned repository, you'll see the data folder here. You can explore the sample data, export it into a CSV. It's not really used, it's just for you to explore it if you want, because it's not, really easy to go and look into the Parquet. But the actual data, the source data for this is coming from a few Parquet files, which are stored in this data subfolder here. And so then the data model gets created, it gets modeled, it gets trained. You can explore the details in the credit model file here. I'll skip this, but essentially building all the features. It separates the training data set and the testing data set, does the training, and then it saves the pre-trained model into a model.bin file, which is essentially the file that keeps the pre-trained model. And so after that, you can actually go ahead and launch the application here. So Streamlit run is the command that you can use to run your application. And if you're interested in to look at how this Streamlit application look like, this essentially is very simple. So you typically use the Streamlit widgets. In order to construct your page, you just pass the parameters, the configuration for those widgets, and you orchestrate them in a page. So again, you don't need to know any HTML stuff or CSS or any type of web development. So you only need to know Python about this. Yeah, so in my case, I'm running Redis locally in the Redis stack container. There is a command to pull and start this container in the README file as well. And Redis stack comes with the tool that's called Redis Insight. So this is the GUI tool to explore your Redis database. And you can see that there's a bunch of hash maps that the feature store got created during the materialization process. It uses its own format, so it's a little bit cryptic. I mean, Feast using its own format to create those hash maps, but you can play with, with this. You can look at currently there's 57,000 keys approximately in there, and you can obviously play with Redis database using this GUI as well. Yeah, so that's pretty much it. I hope you learned something new, and thank you for coming here.
How to break down and ask questions, but so yeah, this is what Redis Cloud practices cloud. But on top of it, there's several other tools, like Streamlit is one of them. Streamlit handles the website, like input and the output, correct? What we saw.
Yeah.
You had
So Feast helps you to orchestrate your features, right? It essentially helps you to organize your data in a way so when you train your model and when you use your model, you're using the same shape, you're using the same quality of the data essentially. So you can think of this as a repository of your data blocks that you're going to be using for training your model and, uh, and for the inference as well.
Okay, this is where what happens if this wasn't?
So if FEAST wasn't there, then a data scientist would typically call a data engineer and say, hey, I want to use zip codes, I want to use past loan approvals information in my model. I want to use this, this, and that. And that will typically come up with, let's say, 20 different fields that they want you to essentially prepare for them so they can feed this data, train this model, and then publish this model for the inference, for the maybe online, maybe batch inference, right? Data engineers will go and prepare this data, but they will apply their own logic to that, right? How they prepare this data. Maybe they will include dirty data into that pipeline, into the final result. Maybe they will change the type of the zip code, make it a string instead of, or make it an integer instead of a string, right? Maybe do some other crazy stuff, right? And it's probably okay before you hand this data over to a data scientist that will figure out and ask you to fix those issues. It's not okay when this happens when the model got trained already. And so once the data is fed into the model, or maybe a developer who's using that model decided to basically to skip zip code when calling this model. Well, and it relies on that feature, right? So it cannot provide meaningful results if the zip code is not provided, right? It can return you some result, but it may be incorrect result. The model would behave differently if you just provided that field to that.
So please allow me to explain this and tell me if I'm right or wrong. This automates some of the some features that are common. Let's say zip code and things associated with common. If it's for you to do just so this information. Am I correct or wrong?
I would say that FEAST allows you to guarantee the reproducibility of the results once you train and once you use the model, essentially.
Got it.
The way it guarantees that by basically having the very clear definition of the features that you're going to be using.
Thank you. Is there any other you forgot like please Streamlit, Redis, and what else do you do?
Well, in this particular demonstration, I think those are the main elements. But in the bigger picture, of course, you would use a whole bunch of other stuff, including those that Nick has mentioned for, operationalizing, productionizing the model, publishing it into the actual production environment, serving, retraining. There's a whole bunch of things that need to be taken into account in order to close the loop using machine learning in production. So it's essentially a pretty complex process.
I'll ask the more questions later.
Yeah, sure.
Anyone? Okay. So just think it's showing that those in production environment, how does that like let's they kind of and they're giving it away. What other versions installed to like this is
Well, you can deploy your model. If I understood your question correctly, you can deploy your model and use multiple sources. As I mentioned, the original database for that was DynamoDB. It's just the latency that was the problem there. And so that's why they decided to test out a Redis instead of, a different database. But you can use Cosmos DB, you can use, your favorite database, um, relational or NoSQL database as part of this. And typically you would have multiple historical data sources providing data to you. But for the online piece, you want to minimize the latency because like I mentioned in the beginning, every layer adds on top of that. And so if you really want to call it a real-time model, you have to have the online uh, store as part of your architecture for, serving the model. Wherever it's going to be Redis or not, it's up to you. If you can tolerate certain latency, it can be a different database. If you want sub-millisecond response time, you probably want to look at something that keeps data in memory, such as Redis, for example.
For Redis, it stores it in memory. Does Redis a distributed database? So if your database is too big to fit on one machine, it scales out to multiple nodes?
Yes. So Redis has a notion of shards. And so essentially, you can have multiple shards spread across different nodes. So it basically scales horizontally. And it can be distributed in a way that you can deploy Redis into multiple regions as well. So for example, a copy of your database can be deployed in US East 1, and another one can be deployed to European region, right? Of course, there's going to be a question of consistency in that case, and Redis Enterprise in particular addresses that piece. Redis open source does not have anything basically to kind of work on that. But yes, the short answer is that you can distribute it and scale horizontally. So potentially you can keep like terabytes of data in there. The cost will become a different question there, but that's certainly possible.
What's the biggest secret you solve with terabytes?
Well, dozens of terabytes, yes. So some big financial organization, they prefer to keep a lot of data in memory because everyone is using, mobile banking these days, and it just has to be, served with a very low latency. You probably noticed, I certainly noticed that you no longer need to give travel notifications to a bank. And the reason is because they adopted a lot of the fraud detection mechanisms that utilize the online predictions, right? And so this is a big area for us at Redis, running, these big clusters of databases, in-memory databases for huge financial organizations, because they pretty much do everything in real time, right? So when you're making transactions, and there's millions of those transactions happening pretty much every minute, you want to keep a lot of data in memory. And so cost has become a big problem here because, of course, when you scale this to a certain limit, you start thinking, okay, that DRAM is actually pretty expensive. And so what Redis engineers came up with is that they said, hey, let's use SSDs, for example. And of course, I'm, going away from that topic, but let's use SSDs for to offload some of the data sets to minimize the cost of in-memory data. But the problem with SSDs is that they have certain cycles, write cycles, and so after let's say 5, 6, 9 months being used in that with those workloads, you just have to replace them. So an interesting thing is that there's a new generation of SSDs that can tolerate a huge number of write cycles these days. I apologize. That's
No, we like this.
but it's a good thing to keep in mind because if you write a lot into something that's not supposed to tolerate it, such as an SSD, like a traditional flash drives, it'll wear out very quickly.
Stephen, I want to ask something.
Yeah, that's just, I don't see any additional questions.
Yeah.